So today we will discuss about the relativistic effects on atoms, meaning when the atom is talking to electromagnetic or any background quantum fields, and if it is moving with respect to a lab observer and moving with relativistic speeds, Schrodinger equations is not supposed to be valid in some sense, because we know that relativistic moving particles are dictated by either Dirac equation or Klein-Gordon equation. Only their limiting case is Schrodinger equation, as we saw. So therefore, how do we correct for the expressions which we obtained of transitions, weights, and transition probabilities, and then how to write down the Lane-Blanc kind of formalism for such an atoms which are moving with finite velocity comparable to the relativistic speeds. So for that, for this point to be addressed, recall till now we have just discussed atoms at rest in the lab frame. Most of the times we had written like the probability of transition of a state of an atom from A to B dictated by the monopole coupling term, squeezed between the state of interest from B to A or A to B, whichever way you want to look at. That will come with a plus minus sign. If B is ground state and A is excited state, a minus sign will appear over here. And if B is excited state, A is ground state, plus delta E will appear over here. And the 2-point correlator of the background field will tell me how much is the probability of such a transition. Okay, so the coupling with the field and the 2-point structure of the field together determine through this integral transform what is the probability of transition. If either of them is 0, if there is no coupling, M is switched off, or the field is having 0 correlations between x and x prime at location T and T prime, at the time location at the time T and T prime, then there is no probability of transition. So this was true for atom at rest we have computed till this time. We just want to see how it will start mattering if the particles are moving as well. So previously we used to write down the 2-point function of the field in terms of its Fourier modes, and in that sense this 2-point function is written in terms of uk at x and uk star at x prime. And if I open in terms of t and t prime and x prime, I will get a e to the power minus I omega k t minus t prime and e to the power I k x minus x prime. It should be x minus x prime as a vector, spatial vector x minus x prime. While this exponential factor was just coming from the operator, monopole operator, its interaction version, Vi, remember, Vi is squeezed between the states of interest A and B. However, what was true while we were doing all this business all along, the T appearing here, 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 or even here, all the times appearing in this game, were the same time as seen by the atom or any observer in the lab. So that means the atom was at rest with respect to lab observer or moving very slow. That means their times were not much different. So this is non-relativistic setting in which we could have written in this way. So the double time integral which appears over here, remember this appeared from the mod square of probability amplitude, and the probability amplitude itself had a single integration in dt which was obtained from the Schrodinger equation. In some sense, writing Schrodinger equation in the interaction picture, but ultimately the Schrodinger equation. So therefore, till now whatever we have done, the basic assumption where the time the atom sees, that means the Hamiltonian time evolution, this time over here or the integration time over here, while the time at which the fields evolve, e to the power I omega t, are the same thing. So this is the description of the field with respect to observer in inertial lab, and this is the time evolution of an atom at rest with respect to that observer. However, if the particles start moving relativistically, then we know already that the time felt by the atom and the time experienced by a lab clock in the inertial frame will become different, and they will precisely become different with respect to this gamma factor. So just to recall things once more, let us say some event happens in the atom frame. Suppose the interaction is turned on and then it is turned off. So some time elapses in atom's frame. So atom sees at time some t is equal to 0, the interaction is turned on, and at time dt, the interaction is turned off. And in this meanwhile, atom is not moving at all in its own frame. So in atom's frame, its displacement in space has become 0, and the total event ds square, or the total separation is the proper time separation between the two events of interaction turning on and turning off. According to atom, this much time might have elapsed, which is the proper time. If the same event is viewed from the lab frame in which the atom appears to be moving, as we know d tau square is an invariant quantity, the lab observer will also ascribe the same amount of d tau has elapsed. So there was some interaction which was turned on, and after a while when atom moves here, the interaction is killed off. In atom's frame, it is happening at its own location, and this much time has elapsed. So atom's clock has shown some time displacement dt atom. While there is an observer which is sitting outside and who's witnessing this atom moving along some direction with some velocity. So the proper space-time interval between these two events should be same as viewed by any observer of our philosophy which we learned. So according to an observer in the lab frame, total time has passed between these two events of interaction turning on and interaction turning off is dt of lab, so dt lab square. But this is also true that these two events of turning on and turning off are not happening at the same place. There is a spatial displacement, dx square plus dy square plus dz square is non-zero in this case, and which is equivalent to the velocity with which atom is moving times the time has elapsed in the clock of the lab. So put together, the same amount of d tau square is generated this time in the lab frame clock by this equation, and therefore you will get that this d tau square is nothing but dt of atom square from the previous expression which we just wrote down, and that should be equal to 1 minus v square times dt square of the lab. So therefore dt atom upon dt lab is 1 upon square root of gamma, 1 upon gamma, where gamma itself was 1 upon square root of 1 minus v square upon c square, of course. When we write down like this, c square division and multiplication is happening all around, which to say we are working in c is equal to 1 units. So you see the dt atom upon dt lab is 1 over gamma factor, and d tau therefore, which is the proper time of the atom, and this is the same dt which is seen, the same proper time is seen from the lab frame, which is small dt. So they are off by a factor of gamma. Okay, so the time spent is less in the frame of the atom d tau, while dt, so d tau is square root of 1 minus v square times dt. So whatever dt you see in the lab frame, the atom feels only a fraction of that, because d tau is 1 minus square root of v square times dt of lab. This is a quantity which is smaller than 1. So therefore, the time felt by atom is the smallest amount of time it feels, while other observers feel that the atom has traveled for a longer time. And in compensate to have that longer time seen, they have some velocity deduction happening to generate the same amount of d tau. So therefore, the distance traveled according to the lab observer is x minus x prime between the time events, which is given as the vectorial difference. Now suppose it is moving in one particular direction, let us call in z direction. So it will be the velocity times t minus t prime, the time difference elapsed in the lab, the direction is z, and velocity c is v. So the spatial separation between the two events is this equation. Now we can convert this t minus t prime into the how much time it has elapsed according to the atom itself. We already know that this is related to gamma times tau minus tau prime, because you see dt lab is gamma times dt of atom. So therefore this is the time separation in lab frame, that will be gamma times the time separation in atom frame. At the cost of gamma, this velocity gets corrected, and this is the event being recorded, the spatial difference as seen in the lab frame. Now, when we had written these integrations, for example, or this m operators exponent, the m operators squeezing which has given rise to this exponential, these were coming from the Schrodinger equation. This portion was coming from the Schrodinger equation, and this portion was coming from the field theory as seen by lab observer. Now, if we keep writing the field description as true for observer in lab, then we have to translate the 2-point correlation into the rest frame of the atom, because the Schrodinger equation is supposed to be true in the rest frame of atom only. Schrodinger equation will not be true to describe the time evolution of the atom from the lab frame, because Klein-Gordon or Dirac equation should guide that. But in the rest frame of atom, because it is not moving at all, it will feel that its own evolution is governed by the Schrodinger equation only. So there is a dichotomy between the time felt by the atoms, which are controlling this portion, while the time felt by the field, which is being controlled by the 2-point correlation, which should be written in the lab frame. So overall, what we have to do, I have to cast everything into the rest frame of atom, where I have everything in Schrodinger picture, because particles are not moving, or hydrogen atom or atom itself is not moving, so its own evolution is Schrodinger equation, at the cost of converting the field correlator, which typically we write in inertial frame of lab frame, in atoms frame itself. So what I have to do, I have to take the 2-point function, which is given in terms of lab clock, and convert it back into the atom clock. So we have already achieved that. We already know t minus t prime, how does it look like in atoms frame, and this x minus x dot, how does it look like in the atoms frame. So both these computations are with us right now. So therefore, I would be able to recast the 2-point function, which was appearing as omega times t minus t prime, which now will be written as gamma times tau minus tau prime, and velocity times t minus t prime it will also be written like velocity times gamma times tau minus tau prime. So suppose particle was moving along the z direction in the k dot x term, which had appeared in the 2-point function. In the 2-point function, k dot x minus x prime appears. Suppose x minus x prime points only along the z direction, as we are considering, only k dot, the z component of this k dot z unit vector will survive over here, which gives you a k mod k times cos theta. So you see, you will get not only k mod k, which is the magnitude of the k vector, the velocity times the gamma factor times the atom's time separation, atomic clock's time separation, times cos theta, because the particle is moving along the z direction according to observer in the lab, observer in the lab, okay, or vice versa. That means it is the k vectors in the space in which the d3k has been written. So d3k again can be written in spherical polar coordinate systems, in which this cos theta will appear. That means the coordinate system is written like this, okay. So the coordinate system is written in a particular way, where the particle's motion direction is identified as the z direction. Suppose initially you had chosen any z axis, x axis and y axis in this d3k, and particle was moving in a particular direction. What you can do, you can reorient your coordinate system such that your z axis has become the particle's direction of motion, and x and y are just orthogonal corresponding coordinates. So therefore, if I do in such a coordinate system, the integral expressions which was over here can be obtained. So integral expressions here can be obtained in this nice way, where I have converted every t minus t prime into tau minus tau prime, which was already there in the exponential of the monopole operator temporal dependence, and here it will become gamma times t minus t prime, tau minus tau prime here, and this should be cos theta. So cos theta should appear here. There should be theta here. So I have converted this t minus t prime, which was appearing in the 2-point function, as gamma times tau minus tau prime. X minus x prime, which was appearing in the 2-point function, can be written as k times v gamma times tau minus tau prime times cos theta. Remember, we had chosen our z axis to be along the direction of motion. So any arbitrary k vector will make some angle cos theta, will keep changing with different k's. So therefore, we have to do integration over theta as well, which is hiding in this D3. All right. So like before, what we will do, we will collect all the tau dependent terms. So here is the tau dependency, here is another tau dependency, and here is another tau dependency, which we club at one place, and it becomes one temporal integral 0 to capital T of d tau. And what are the functions? Exponential minus iota delta E upon h bar, which is appearing over here, minus iota delta E upon h bar, plus whatever is appearing, this gamma omega k tau minus kv gamma cos theta tau, that I am collecting at one place and calling it as omega k prime. So this is omega k prime. Omega k prime is nothing but gamma omega k minus gamma kv cos theta. Now we can club the k and cos theta together to call it the z projection of the k vector kz. So effectively it becomes gamma times omega k minus kzv. So you see, this is exactly the Lorentz transformed frequency as seen by the atom. If omega k was the frequency as seen in the lab frame, and kz, k cos theta, was the kz z projection of the spatial k vector in the lab frame. In the atom's rest frame, the frequency will appear Lorentz boosted, and this exact formula, which we had seen in week 3's discussion as well, connects the atomic frequency, the frequency of mode seen by the atom, rather, not atomic frequency. Atomic frequency is delta E upon h bar. The omega k prime is the frequency of the field mode as seen from the atom's frame, and it is related to those quantities as seen from the lab frame. Okay, so this is fine. So this is all so far so good. We have very nice relation which has appeared in the exponential. So if I do the time integral, again, you know, this is going to give me sinc function, sine of this argument divided by the same argument by 2. So, and this will also give the sine function with opposite phase, so that you will have a probability sine square of delta E plus omega k divided by delta E plus omega k prime. So h bar is there. Okay. So this is what it would give you, and in long time limit we know that sinc function becomes a delta function. So again it will become a delta of delta E upon h bar plus omega k prime mod square, and the integration is happening over d3k prime, d3k upon twice omega k. So what has changed slightly is omega k was appearing previously when we did for non-relativistic moving particles. This time its boosted value comes and sits here, and similarly in the second integral. However, the integration is happening on the mode function distribution in the lab frame, because that is how we had written in the field decomposition in terms of lab modes. And omega k and omega k prime and those quantities are connected by this Lorentz boost equation we had just written. Okay. So just let me write once more for clarity. Here is cos theta, which we have to put it down. Yeah. So omega k prime is different compared to omega k, while the integration is happening over d3k upon 2 omega. Okay. However, despite the fact that the omega k prime and omega k are changing from frame to frame, the relation between omega k prime and k prime and omega k and k remains the same. That means in the lab frame I had a relation that omega k is square root of k square plus m square. Despite the Lorentz boost has shifted their individual component values, this relation still remains true in the atomic frame. But omega k prime will still be square root of k prime plus m square. So that means omega k prime's lower value is m and upper value is infinity. So this integral, whatever is appearing inside the argument of a delta function, is delta E plus h bar plus omega k prime. This omega k prime is positive semi-definite. This is also positive semi-definite. So therefore the delta function is also positive semi-definite, and therefore it will vanish. So therefore, even though the atom perceives the field mode slightly differently and hence perceives the 2-point function slightly differently, the probability of absorption through vacuum fluctuation still remains 0, which was the case even for non-relativistically moving particles. Now that particles have started moving relativistically, it is suffering some amount of boost in terms of frequency and its mode functions description, but still it is not sufficient to cause a transition from ground to excited. So that feature remains true even for relativistic fields. Now what about spontaneous emission? Suppose the particle or the atom itself initially is in the excited state, and then we are trying to compute the probability of going into the ground state through the vacuum fluctuations thing. Remember, this time atom perceives the vacuum fluctuation slightly differently through the change in the mode function. What will happen? The delta E terms would flip a sign, because we know in terms of here when we are looking for spontaneous emission, a minus sign gets replaced by plus. So therefore, the integrals what are appearing over here will just become overall delta E term will flip a sign, all other terms will remain the same. So you can see with this structure where delta E undergoes a sign flip, this exponential here becomes e to the power iota delta E minus omega k prime, and this thing is complex conjugate of that at different tau prime. So if we know the protocol already, in the large time limit, it will become a double delta functions with arguments appearing as delta E upon h bar minus omega k prime and delta E upon minus omega k prime, h bar upon delta E upon h bar minus omega k prime twice. However, as we see again, the integral is happening over d3k upon twice omega k, while these delta functions, which now can survive because this argument is not always positive. Whenever omega k primes become delta E upon h bar, then it survives. So what I have to do, I have to put it wherever the roots of this solution over there, that will go and sit over in the twice omega k over here. Omega k has to be first written in terms of omega k prime, and omega k prime is equal to delta E upon h bar, and we will come over here and sit. And similarly, d3k has to be converted into d omega k prime. However, we know this. So on face of it, this expression looks slightly different. In the non-relativistic case, or in the lab frame, if an atom is stationary, then the expression will not have a primed sign here. It will just be this thing which we had previously obtained for an atom at rest in the lab frame. If atom is moving, omega k has changed to value omega k prime. So integration will slightly change on face of it looks like. However, it is not going to be the case, because you see, even in the Lorentz transformation, d3k upon twice omega k is a Lorentz invariant quantity. This is Lorentz invariant measure. So that means d3k upon 2 omega k is also equal to d3k primed upon 2 omega k primed. So we can safely replace this d3k upon 2 omega k appearing as d3k primed upon 2 omega k prime. And then you see the integral is exactly the same what we had obtained in the non-inertial case, non-relativistic case, when particle was at rest in the lab frame. Okay, this becomes just a dummy variable. Omega k primed is just a variable transformation. In the lab frame, no primes were appearing. It was omega k, omega k, omega k here, and d3k here. This time, all it has happened that every k thing has picked up a sign, a prime. That prime is just a relabeling, calling k as x prime. This is not going to change the value of the integral. So therefore, the probability of transition will not change at all. And this is not a surprise, because it is actually a computation in the inertial frame in which atom is at rest. This is atom's rest frame. So in this frame, atom is still at rest. So therefore, probability should not have changed. Why should two inertial frames become different if we are looking at the same exact process? Okay, and probability is a number. Those things are supposed to be Lorentz invariant. Probability should not, number of some transitions which is dictated by probability should not change from frame to frame. Okay, if suppose I start with 100,000 atoms in excited state, and there is a 30% chance of spontaneous emission, that means after a long time I should get 30,000 atoms in the ground state and 70,000 in the excited state or so. This ratio should be same in all inertial frame. It is not that the atom in a ground state appears as excited state to some other inertial observer. So therefore, the probability should not change from frame to frame, and this is exactly what we have obtained. The probability of transition of an atom at rest does not change from one inertial frame to another inertial frame. Previously, we had computed things for atom at rest. Now we have computed things for probability as seen by the atom, which is still the computation fundamentally in an inertial frame of an atom at rest. So therefore, this is not supposed to change. What will change would be the rate of transition. So again, if I have to write down the rate corresponding to it, I will convert this double delta functions into their sine functions for form. It is just a limiting case of sinc function, if you recall. And using that, we have already done that before. If I take the derivative with respect to time, I will get this expression. Just a quick summary how to see that. The double delta function which has appeared can be nicely broken into a single delta function and one limiting expression. This is also a delta function, but I am writing it in a limiting fashion. And call this as some f of omega k, let us say. Now use the property that delta of x minus a times fx gives you the delta back, but f can be replaced with the argument of the delta function of 0. Okay, so that means I can write down the argument of delta functions 0 is this delta e upon h bar minus omega k should be 0. So therefore the sinc function's argument appears vanishing. So that's what we can do. So I can write down the twice sine upon this object sinc function like this. And when I supply the argument of delta function into this function, I will just get a t outside. Okay, and again the delta function is delta e upon h bar minus omega k naught, a factor half. Using the property of the delta function, which is this, we can write as twice of delta function with argument half went away. Okay, so this is just a simple algebraic exercise one should be able to do to prove this. So this is the rate of the transition. Again, you will realize that it is exactly the same expression which we had obtained for atom at rest, and no wonder, this is again a rate as seen by the atom's clock. This rate dt is being, remember the t was the upper limit of time interval as seen by atom's clock. So again, the rate is being calculated by an observer who is co-moving with the atom. That means the atom is not moving with respect to it, and it is an inertial observer. So again, it is the same computation of a rate of a stationary atom in an inertial frame. So it should not have changed, and it does not. So you get the same expression back. However, now a crucial question comes that what is the rate as seen by the lab observer? This rate is seen by the atom. Atom will feel itself will make a transition at a rate which was commensurate with non-relativistic rate. However, if we want to obtain the rate of transitions as seen by the lab observer, it will be the number of transitions or probability, the derivative with respect to lab time. Use the chain rule. First obtain the derivative with respect to atom's time, and then the atom's time with respect to the lab time, dt upon dt lab. And that we know it's already 1 over gamma. So you will get the atom's rate multiplied by 1 over gamma, and since gamma is 1 over square root of 1 minus v square by c square, this factor is smaller than 1. Okay, so therefore the rate as seen by the value of rate as seen by the lab observer will be smaller compared to what atom sees. This is again natural explanation exists because same number of transitions are happening in large amount of time as seen from the lab clock. So therefore the rate would be slightly lower. Okay, so this all has happened because the moving atom perceives vacuum slightly differently, but still a vacuum and quantum fluctuations, and it derives the same expression for the non-relativistically moving atoms computation. However, when we go to the lab frame, we have to just do the Lorentz transformation from the clock rate from one frame to another frame, and that's why this extra gamma factor comes about. All right. So this is the way we typically will work out. As we discussed, this projection psi is not a good measure of probability because its local value, the density, probability density is not a good measure in relativistic case. Klein-Gordon equation does not support this definition of probability, let us say, in subsets. So therefore, the trace condition in the Lindblad and whatever we learned, which was trying to protect the psi tilde trace, that is suspect because this is not really enforcing for relativistic particle because they do not comply with this definition of probability. So either we'd go and develop a new theory of Lindblad formalism, or we jump to the rest frame of atom itself. There everything becomes non-relativistic, apply the Lindblad formalism, do all our computations, and at the end of the day translate everything back into the lab frame, just like we did. Here we computed the rate and everything by just doing non-relativistic computations in the rest frame of the atom, and once we had the result, we transported them back into the lab frame using the Lorentz transformation. So that is the strategy most of the time it's very useful in dealing with, and in not only relativistic transformation, non-inertial transformations as well, which is not a mandate of this course. There also the same philosophy is applied, and people try to obtain the behavior of atom or the structure of transitions in non-inertially moving particles as well. Okay, so we will keep this notion in mind that first we will jump to the rest frame of atom, do all our computations, and then we will transport the results back into the lab frame. Only thing we have to be careful about when we go to the rest frame of atom is that in the expressions of transitions and everything, one bit, which is the monopole operator's temporal evolution, the exponential with delta E upon h bar in them, this is written in terms of atom's clock, and when we write down the mode function of the 2-point function in terms of mode function, this is written in terms of lab clock. So we have to properly transform these two things and write down the correct version of physics which we want to. Okay, so we stop over here for this class. In the next discussion session, we will see the usage of this in determining the quantities of characteristics of atom itself. Till now we have just looked for transitions, but we know that if there is fluctuating Hamiltonians or time-dependent Hamiltonian, it also tries to change the eigenstate description as well. The eigenstate do not remain eigenstate anymore. When time translational symmetry is broken, then there is no eigenstate, and therefore the energy gap between the atoms will also keep changing. The delta E is not a protected quantity over time because atoms' eigenstates are not eigenstate of the full Hamiltonian anymore under the action of a fluctuations. Those things we will see in the next class. So therefore I stop over here.